So immediately after this, the objection to the factoring paper was, but you can't do error correction on a quantum computer. And if you want to factor a real number, you know, if every quantum operation, every quantum gate is not accurate to one part in 10 to the 9th, the errors are going to mount up and the result will be worthless. So, and why is this? Well, somewhere we have the no cloning theorem here. Errors. So what you can do is you can look at the classical techniques for error correction. Classical fault tolerance. And there are a bunch of techniques for classical fault tolerance. One, checkpointing. And write down state of system. If something goes wrong, you don't have to start at the beginning. Don't have to start at the beginning. Go back to beginning. And I don't know what it's like now, but in 20 years ago, if you looked the advanced micro devices chips had checkpointing. Every so often they wrote down, and they called these techniques the little hammer and the big hammer. If something went wrong, they started again at the checkpoint. And actually, both the little hammer and the big hammer were checkpointing, and I forget which one was. I forget what the difference between them was. And they, whoever told me about this, strongly suspected that the Intel chips also had this cheat in them. So the chips don't actually work perfectly, but you don't notice it because there's fault tolerance built in. There's another technique, error correcting codes. And you map k bits to n bits, and you can recover from some number of errors. And these are really good for memory and for communication. So basically, all your computer memory and all your electronic communication uses error correcting codes. But classically, nobody used error correcting codes to do computation. And then 3, massive redundancy. So what you do is you keep many copies of your computation around. And if one of them goes wrong, you compare them with the others. Or rather, you keep comparing them. And if one of them is different, you throw it out and copy the state of one of the other computations. And you can do massive redundancy for each bit, or you can do massive redundancy for the whole computation. Yeah?
So in the case of massive redundancy, it's relatively obvious when an error occurs.
Right.
In the other two, are we assuming that there's some method of error detection in place?
Yeah, well, error correcting codes have a method of error detection. Checkpointing, yeah, you can really only use that if you have some method of error detection, but I'm not going to get into what method of error detection you use for it because I just want to ask which of these are compatible with the no cloning theorem. Well, massive redundancy. it's fine to start out with n copies of your computation. It's fine to compare them against each other to see if they're wrong. But if one goes wrong, what you have to do is copy the state of another to this new one, or else you just have n minus 1 copies of your computation, and number of copies of your computation or number of copies of your computation without any errors just keeps go down. So this does not work. Checkpointing, well, you want to write down the state of your system. That's copying it. The no cloning theorem says you can't do that. Error correcting codes, well, it looks like they're also forbidden by the no cloning theorem. But in fact, they work. And you can use them to do computation with, as well as use them to do communication and memory with. The reason nobody does computation with them in classical computers is that it requires a lot more overhead than using them for communication and memory. And classically, these techniques are much less resource intensive. But they work for quantum computers, and we will talk about them in the third section of the class.